All right, let's get started. So this is week 3, and in tonight's workshop, we are going to be looking at confidence intervals, and we will perform one sample hypothesis test. So a couple of quick definitions. What's a point estimate? It's a single value of a statistic, for example, the mean of a sample from a population. Interval estimate is the range of values that is likely to contain the population parameter, or the mean. And that's what we're going to be doing tonight. We'll look at how to find an interval estimate, how to find the confidence interval, which will contain the population's mean or the proportion. Okay, so before we actually go into the math of confidence intervals, let me just give you a quick explanation of what confidence intervals are. So let's say I want to find the mean weight of all the apples in an orchard. So instead of getting all the apples and then weighing all of them, that's going to be a lot of work and practically impossible. So what we will do is we'll take a sample and we'll calculate the mean weight. And let's say the mean weight was 149 grams. Using this information, if I extend this information, if I can do some math, and if I can predict like a range of values that will have my mean of the entire population of apples in my orchard, that would be the confidence interval. And the way I will do it is I will take this mean weight, 149 grams, and then I will do some math and I'll come up with something called the margin of error. And let's say my margin of error came out to be 2 grams. So I will add and subtract 2 grams from this 149 grams, and I'll come up with a range of numbers. So if I subtract 2 grams, 147, and I add 2, it is 151. Now I can say that the mean of all the apples in my orchard is somewhere between 147 grams and 151 grams, provided, of course, that the sample that I have is representing my population pretty well in terms of the size and the variation. So this range of values is called my confidence interval. And usually with confidence intervals, you might have seen already that there is a certain level of confidence. We either say 95% or 99% or 90%. So we'll talk a little bit more about that, and then we'll also look at how to find the margin of error. But in short, the confidence interval is nothing but a range of values which will contain my population's parameter. Could be the mean or the proportion. There is no fixed sample size needed. We just want to make sure that our sample is representing our population well. And definitely, if it is going to be a large orchard, I definitely want a large sample because only then it will represent my population. The smaller the size, obviously, my values may not be as accurate as I want it to be. So this is just a write-up of what I just explained. So I add and subtract 2 grams, and I have 147 to 151 as my confidence interval. So what affects the width of confidence intervals? My sample size and my variation. How does variation affect my confidence interval? I want to make sure that the apples that I have are representing my population well. So if I pick all small apples, the mean weight is going to be small. So the confidence interval that I come up with may not be an accurate one. So I want to make sure I have a mixture of different sizes in my basket. So if all the apples are medium and above medium in their weight, then obviously the mean that I calculate and consequently my confidence interval will be more accurate. So a confidence interval provides a range of values which is likely to contain the population parameter of interest, the mean or the proportion. Confidence interval is given by the point estimate plus or minus the margin of error. Point estimate is nothing but the mean of the sample, mean or the proportion of my sample. So if I add and subtract my margin of error, I will get my confidence interval. And my margin of error is the critical value times the standard error. We will look at the mathematical part of it in the next slide. So with confidence intervals, we usually have a value associated with it, like a 90% or 95%. What does that mean? When I say that I'm constructing a 95% confidence interval, I'm constructing an interval where I am 95% confident that it contains my population's parameter, the population's mean or the population's proportion. So if I construct a 90% confidence interval, I'm 90% confident that my population's mean will lie in this interval. In other words, if I were to take 100 different samples from my population and I construct confidence intervals for each of those, 90% of those or 95% of those will have my population's mean and only 5% will not have it. So below here is a picture where you have the population's mean, mu, and for 20 samples, the blue vertical lines are the confidence intervals that have been calculated for 20 different samples. And you see, out of the 20, there is only one which does not contain the population's mean. So if I were to extend this for 100 samples, then there would be 5 which will not have the population's mean. So this would be my 95% confidence interval. Now let's look at the formula. So the confidence interval for the population mean is given by x bar minus z star sigma over square root of n. That's the lower value. The upper value is x bar plus z star sigma over square root of n. X bar is the sample's mean. Z star is a critical z value. Sigma is the standard deviation of the population. And n is my sample size. So the second term, z star sigma over square root of n, that is my margin of error. And if I were to take only the sigma over square root of n, we call that the standard error. So the standard error times the critical value will give you the margin of error. So here you can see in the picture here, x bar is the mean of my sample. And using this mean, we will calculate the confidence interval. So you can see it goes from x bar minus m. M is the margin of error. And it goes all the way up to x bar plus n. So this interval will contain the population's parameter up to a 90% or 95% confidence level. And the remaining, you can see in the graph, the remaining part is marked as alpha. Alpha is called the level of significance, and we will be needing that when we do a hypothesis test. So I will refer back to this, the confidence level and the level of significance, how they're related. If you add up the confidence level and the level of significance, it will be equal to 1, and that's your entire graph. So if you know one, you can find the other. So here I have a table with some common levels of confidence and the corresponding critical z values. You don't have to memorize them, but you can always refer to a table in your Xi books whenever you're doing these problems. So what's the Python code? So we import scipy.stats as st, So SkyPy.stats is a Python module that you're going to import, and we're going to import it as st. So wherever we need to use it, we will replace it with st. So then we do print st.norm.interval, and the function takes three values: the confidence level, the mean, and the standard error. So the standard error is nothing but sigma over square root of n. So if you can compute sigma over square root of n and then plug in the values, this function will give you the confidence interval. Any questions so far? Sigma is the standard deviation of the population. So let's do an example. This is from Zybooks. Suppose the mean final grade is estimated for all introductory statistics classes taught at a particular college. The population standard deviation is 4. The final grades for a randomly selected statistics class with 9 people are given. Find the 95% confidence interval for the mean final grade. So we have the formula. So the first step would be to just note down what are the things that we have from our formula. So the mean is given, the sigma is given, we know the n is the sample size. So in this case, it would be 9. We have the values, so let's calculate the mean. So add up all the values divided by 9. That should give us the sample mean. Standard error is sigma over square root of n. So sigma is 4 divided by square root of 9. Yes, sigma is the standard deviation of the population. So you will see there's a difference. When you do z confidence intervals, we will be using sigma, which is the standard deviation of the population. But when you do t confidence intervals, sigma will be replaced with the sample's standard deviation. So you won't see sigma there, you will see an s in the formula. So we will come to that. But whenever you do z confidence intervals, it will be sigma. So for 95% confidence interval, the z critical value is 1.96. Yes, that's correct. The standard deviation tells you how far off the values are, how dispersed the values are, or how scattered the values are from the mean. Yes, the critical values are the same. They will not change. So for 95% confidence interval, the critical value will be 1.96. Standard error is sigma over square root of n. So sigma is given to be 4. N is the sample size. So number of values in a sample, that's 9. So if you plug in that and do the math, you should get 1.333. Sigma is given in the question. It's given that the population standard deviation is 4. You will not be required to calculate sigma at any time. It will be given to you. So from the confidence level, you can get the z value. The way we do it is, if you look at, let me just go back to the previous slide. Might be better maybe if I draw it. Let me go to the next slide and let me draw it. So if I have, say I have my bell curve like this. If you remember last time we were talking about the empirical formula, and then we talked about how the values lie between a certain range. We say 68% lie between one standard deviation, 95% lie between two, things like that. So what you do is if you have the center, which is your mu, and if I were to calculate the 95% confidence interval, I'm trying to find the area under the curve which covers 95%. And the value for that here would be negative 1.96, and on the right it would be 1.96. That's my Z critical. So for 95% confidence level, if you calculate the Z, it will be 1.96. You don't have to do the math. But in a standard normal curve, if you were to do, for example, the 90%, then you are actually marking off the 90% value in your graph. So 90% of the values are included between these 2 points, and the value of Z at those 2 points would be 1.64, I think. Did that make sense about the confidence levels? How I got the Z? You don't have to actually remember these values. They will be mostly given to you, or you can always refer back in the table. But the thing you want to remember is in your bell curve, you mark off 95% area of your curve. The two endpoints are the Z critical values. Yeah, the thing is when we're talking about the standard normal curve, if you remember, we talked about how all the values in the standard normal curve are Z values. So imagine all Z values here in my horizontal line. If I mark off 2 points such that the area under my curve is 95%, or say 0.95, if my actual value is 0.95, then these two endpoints would be negative 1.96 and positive 1.96. For 90%, it will be different, it will be 1.6. So then you are marking off two endpoints such that the area under the curve is 0.90. You don't have to worry about the math. If you're really interested in the math, I can send you some videos after our workshop. But if you can just refer to the table, for those of you who don't want to go into the math, if you want to just refer to the table, for 95% confidence interval, it's going to be Z is going to be 1.96. If you want to just refer to the table, that should be fine. Yes, I will send you that after the workshop. I messed up the slide. All right. So then you have your margin of errors, which is going to be Z star times sigma over square root of n. So we found the standard error, which was 1.333. Multiply that with the Z star value. That would give you the margin of error. So there are two ways of doing confidence intervals. You can either do the math, you can just do it manually. You can also use Python. I will show you both the ways, but the preferred way would be to just use the Python, where you just find the standard error and then use the Python function. So the Z star, the value of Z star will depend upon your confidence level. If you're talking about a 95% confidence level, then your Z star value will be 1.96. If you talk about 99%, the value will be different. So depending on the confidence level, the Z critical value will vary. So we got the margin of error to be 2.613. So now what we want to do is add and subtract this value from the mean to get your confidence interval. So when you add and subtract, you get two values, the lower the lower bound and the upper bound. The lower bound is 80.60 and the upper one is 85.835. So this is your range. This is your confidence interval. So you can be 95% confident that if you were to calculate the population's mean, if you were to calculate the mean of all the scores of all the students, then it would lie in this interval. So you're using your sample to find a range of values that will have the population's mean. So the Python code st.norm.interval. So you put in the confidence level. So we say 0.95 as a decimal. The second value is the mean. And then third value is the standard error. And if you run this code, you should get the same values that you got when you did it manually. So let's go to Trinket and let's try this out. And for those of you who are just joining the session, if you can enter your email in the box below, I will send you the recording after the workshop. So here we want to look at line number 7. Line number 5 has the import. Line number 7 has st.norm.interval, and I have the three values. So we get 80.609 and 85.834. I usually round it up at the third digit, but if you are required, the question says round it up to 2 digits, then you can just change it accordingly. So let me go back. Okay, here's an example for you to try. I will give you a few minutes to try this out and then we will discuss the answer. Suppose we want to find the mean height of all 10-year-old boys in a city. We choose 50 boys at random and measure their mean height to be 138 centimeters. The standard deviation of boys' heights is 8 centimeters. Calculate the 95% confidence interval for the mean height of boys in the city. So the formula is there. The mean is given 138 centimeters. Population standard deviation sigma is 8. Sample size n is 50. So for the 95% confidence level, the Z critical is 1.96.